When you take a photo with your phone, you're taking an image in 3 colors: red, green, and blue. Your phone camera does this because it mimics how we perceive the world with our eyes. But there's a lot more information than just visible wavelengths of light. This additional information at other wavelengths is extremely useful when trying to see in the dark and find potential threats. Our sponsor, BAE Systems, asked us to design a system which combines information from different wavelengths to give a more complete picture of a background scene and identify people or items that don't belong. This is a powerful approach used across industry called multispectral imaging. For example, if I step behind a bush or into a shadow, a conventional camera might struggle to see me. However, in the thermal infrared, I show up perfectly. Multispectral imaging also helps us sort between different types of objects. Objects have unique spectral signatures. For example, while you know I look different than a tree, my computer has no idea unless you teach it. You could use a neural net to recognize my shape as a person, but that won't help if it's too dark to see anything with a normal camera. The thermal camera sees objects at different temperatures as different brightness values, causing me to show up at roughly body temperature, while a tree will not. I look like me, while a tree will be some combination of brown and green in the visible. When we do this comparison between all 5 wavelength bands, we have more information to detect with. Using the power of multispectral imaging, our system can detect objects over a wide variety of scenes, display them on a GUI, and even film the introduction of a senior design video.
Simply put, our project goal is to autonomously detect people moving within an area for at least an hour using multispectral imaging. To do this, we use thermal infrared, near infrared, and visible wavelength bands to monitor a 75 by 5 by 10 meter region starting from 50 meters away. We call this region our field of regard. We must refresh imagery of our field of regard at least every 30 seconds. The system must detect objects during both day and night and in both rural and urban environments. This requires us to be able to detect people in a wide variety of lighting conditions, from a bright, busy day on the U of A campus or a dark, serene night. Detection must be real-time, flagging individuals within 1 second of image capture. Any good detection system must be able to avoid both false positives and false negatives. This requires careful balancing of detection software to make sure we flag everything we need to and nothing we don't. To have powerful, real-time detection capabilities, we must have both simple processing and accurate detection. This requires us to make trade-offs between detection accuracy and detection speed to ensure we meet both requirements. Finally, we need to display and log flagged objects in a graphical user interface for later user review.
With those requirements, we started with the optical system. Since we have 3 different wavelength regions to cover, and not every camera can see every color of light, we need 3 different cameras to see all of our required wavelengths. 1 monochrome, which can see the near infrared, 1 RGB color, and 1 thermal infrared. We need to see in rural, low light conditions, so our cameras need to be highly responsive to light. We perform modeling on possible camera options to simulate how they would respond to different light conditions. Simply, we quantify the amount of light reflecting off a person at night before seeing how our optical system would collect that light and how our sensor would respond to it. This led us to choose consumer astrophotography cameras since they're already optimized for these low light conditions. A single image can easily cover the entire height of our field of regard, but the width is a bigger challenge. If we use a camera that can see the whole width, a person will be only a few pixels wide. We also have to update the field of regard at least every 30 seconds. We did extensive prototyping and modeling, trying to maximize the number of pixels across a person per detection, while trying to minimize the scan time across the scene. We ended up settling on a design that uses 5 images that we cover in a raster scan.
Since scanning across field is required, all cameras must be mounted on a motorized rotation stage. After calculating the positional and angular tolerances of the cameras, we determined the optimal design was to stack the cameras vertically. This configuration minimizes translational movement of the cameras relative to one another during rotation. We also designed our system to have loose tolerances for easy manufacturing that we were able to machine here at the Engineering Design Center.
The electrical system runs off a single standard wall outlet. A surge protector branches off into 2 main areas. First, a 24-volt power supply feeds our motor driver, which allows control of our rotation stage. Second, a USB hub serves as a central link between our 3 cameras. Finally, we can plug in our laptop using USB-C to gain control of the system.
How do we actually detect objects in our field of regard? For this project, we use statistical processes using no deep learning or AI. We start by modeling the background of a given environment. To do this, we take pixel values from all 5 wavelength bands, looking at the same point in space. We do this for all points in the image, and then look at the relationship between each of these bands. As an example, consider the red and green bands. If we plot pixel values from the background, we then see that when the red values are low, green values are also low. And when the red values are high, green values are high. This indicates a strong positive correlation between 2 bands. Using this relationship, we define what a normal background looks like. Now, when a new object enters the field of regard, we compare it to this expected relationship. If it breaks that correlation, we label it as anomalous. We measure this using the perpendicular distance from the expected correlation. The stronger the correlation, the more weight the distance has. That is, when we have a good understanding of what the background looks like, a pixel being a bit different means a lot. Now consider a different pair of bands, say blue and monochrome, which could have a weak correlation. In this case, there isn't a clear relationship between the two. If we look at the same anomalous pixel, it appears far less unusual in this space. That's because weak correlations produce a wider distribution, so it takes a larger deviation to be considered equally anomalous. If uncorrelated bands don't help as much, why do we have them? From environment to environment, correlations may vary due to scenery or brightness value changes. In the desert, red and green bands might be highly correlated, but on campus, this might not be true. With many bands, we're bound to have a few strong relationships. In total, we analyze all 20 pairwise combinations between these 5 bands. To determine whether a pixel is anomalous, we combine the distances from all these relationships into a single metric called Malhabov's distance. For example, in this image, each pixel receives a score that reflects how unusual it is compared to the background. Finally, if a pixel score exceeds a chosen threshold, we label it as anomalous. And when multiple anomalous pixels cluster together, we identify them as an object.
For hardware interfacing, our system integrates the RGB, monochrome, and thermal infrared cameras along with the rotation stage over USB. The rotation stage controller and driver is operated using the PyTick Python API. The RGB and monochrome cameras communicate via vendor SDKs exposed through virtual COM ports, enabling configuration and image streaming. The thermal infrared camera interfaces using its vendor SDK to access real-time frames built on top of a UVC stream. All devices are connected through a powered USB hub and are synchronized in software to align stage motion with image capture. This allows our optical, mechanical, and electrical systems to interface with our anomaly detection and GUI. Our GUI was designed to be intuitive for a non-technical user to interact with it. It allows the user to change system settings and view the field of regard with a selected camera, such as the RGB, monochrome, or thermal infrared. It flags objects in these images and logs those images and detected objects for later review. It also shows many system runtime statistics, such as total runtime, time per scan, and image processing time to verify we met our requirements. As you can see, we were successful in meeting all of our time-related requirements.
Since we were proceeding well with our requirements, we began working on our stretch goals, of which we have 3. Detect a drone, track an object, and identify a person. These require us to add additional software functionality and specially tune our detection algorithm. As of recording this video, we have successfully detected a drone and are hard at work at the others with hopes to complete them by design day.
Through all of our extensive engineering and modeling work, we not only met all 20 system requirements, but did so with substantial performance margins across the board. We successfully imaged the entire field of regard in every required wavelength band, while exceeding our field of regard requirement. Our processing time averaged 0.4 seconds, over twice as fast as required. Most notably, the system significantly outperformed our accuracy requirement under all of our challenging lighting and environmental conditions, demonstrating the effectiveness of multispectral imaging. At Design Day, we are delivering a fully integrated, highly versatile, and powerful field-ready system.